Everything I'll speak about today is joint with my student Stephen Karp, who, by the way, is graduating this year. Okay, so first let me just sort of give a verbal introduction to the amplituhedron. So it was introduced by Nima Arkani-Hamed and Jaroslav Trinka in 2013 to study scattering in n=4 supersymmetric Yang-Mills theory. Here the amplitudes are complex numbers related to probability of observing a certain scattering of n particles. And since 2005, these amplitudes have largely been computed by way of the so-called BCFW recursion, Brito, Cacciazzo, Fang, and Witten. And then a few years ago, their recursion was reinterpreted by Nima and 5 others in terms of the positive Grassmannian. So in 2013, so basically, the way they reinterpreted the recursion, they said, OK, you can compute these scattering amplitudes by integrating over some kind of collection of cells in the positive Grassmannian. But these cells didn't seem to have a very nice geometric relation to each other. They were sort of far apart within the positive Grassmannian. And the idea of Arkani-Hamed and Trinka was that there should be some nicer geometric object where you can see everything taking place, just one geometric object as opposed to a collection of cells. And so the amplituhedron is what came out of that idea. OK, so that's pretty much everything I'm going to say that has anything to do with physics. And now I'm just going to give a math talk about the object they introduced. And by the way, everything in this talk should be completely elementary, so please interrupt if you have any questions. I'm really not going to assume any background at all beyond sort of familiarity with linear algebra. So. OK, so just to set up notation, the Grassmannian GRKN is the set of subspaces in, say, Rn of dimension k. And to be really concrete, we're going to view points as matrices. So we'll view a point as the row span of a full rank k by n matrix. Maybe I'll call it Z. And now, given a k element subset of the numbers 1 through n, we're going to talk about Plücker coordinates. So delta j of Z is going to be the k by k minor. So the determinant of the k by k submatrix of Z located in the column specified by J. So this is called a Plücker coordinate. And together these Plücker coordinates give the what sign convention? Oh. I'll just read them from left to right. Yeah. So this gives us the Plücker embedding into projective space of dimension n choose k minus 1, where we send our matrix to the collection of all Plücker coordinates. OK. And now the totally positive, or TP, respectively, hi. Totally.
You to leave now because you're done with the physics.
Yeah. The totally non-negative Grassmannian. So, and okay, let me write down my notation. So the totally positive part is GRKN with a greater than 0, and the totally non-negative part is the subset of the real Grassmannian such that all of our Plücker coordinates are strictly positive, respectively non-negative. Right, so we have this embedding of the real Grassmannian into projective space. Of course, we're in projective space, so signs only make sense up to a global scalar factor. So when I talk about the totally positive Grassmannian, this means the set of elements in the real Grassmannian where I can choose a representative with all Plücker coordinates strictly positive. And the totally non-negative part is the subset of elements of the real Grassmannian where for every element I can choose a representative with all Plücker coordinates non-negative. So since 2003 maybe, there's been a lot of work on the totally positive and non-negative parts of the Grassmannian. I'll just say a few things about it. So there is a beautiful explicit cell decomposition due to Postnikov. And what we can do is the following. So if script M is a collection of k element subsets of 1 through n, then we're going to define the positroid cell S, M, T, and N to be the set of all elements in the non-negative Grassmannian such that my Plücker coordinate delta I of A is strictly positive if and only if I lies in my collection.
When you're writing n choose k where n is a set, just to make sure, you mean all k size subsets of that?
Yes. So yeah. Sorry. So bracket n means the numbers 1 through n, and bracket n choose k means all k element subsets of 1 through n.
Okay. It seemed clear from the context. I'm not familiar with the notation.
Okay. Right. So this cell is just the set of all elements in the non-negative Grassmannian where my Plücker coordinate is strictly positive if and only if I lies in M. And then this subset is either empty or it's a topological cell. It's homeomorphic to a ball. And so, of course, this gives us a partition of the non-negative Grassmannian into cells. And we've just partitioned it into pieces based on which Plücker coordinates are strictly positive and which are not.
So if all of them are strictly positive,
that recovers. Yes. So so there's one top dimensional cell, which is the totally positive Grassmannian, and then the totally non-negative part is the closure of that. So Postnikov gave this cell decomposition and also gave.
Ones also cluster varieties, or?
So yes, this has been shown by work of Leclerc. Yes. Sorry? The question was whether all of these cells have the structure of a cluster variety, or say if you take the closure, and the answer is yes.
Is each term the closure what we expect?
Sorry?
Does one know if each of the closure is what we expect?
Yes. So yes. So the closure is exactly what you expect. Yes. Totally non-negative.
Oh.
So
Yeah. Yes, yes, it is known. It is known for which M this is non-empty. And basically, Postnikov gave a family of combinatorial objects which index those cells, meaning the non-empty ones. About the topology of this space, it is conjectured but not known that the whole totally non-negative thing is homeomorphic to a closed ball. So that's unknown. However, it's known that the phase poset, a closed ball. However, it's known that the phase poset is a combinatorial ball. So that's something I showed a while ago. And it's also known that the whole thing is contractible with boundary a sphere, homotopy equivalent to a sphere. And the same is true for the closure of any cell. And as was alluded to by Shankil, there's connections of this object to cluster algebras. There's also connections to soliton solutions of the KP equation. And now there's connections to scattering amplitudes. OK, so any other questions before I go on to define the amplituhedron?
These connections to cluster coordinates you said were described before the scattering amplitude picture? Because the scattering amplitude picture has some links to cluster coordinates, so it's
right.
the same one, right?
So the I think in 2002 or 2003, Scott showed that the coordinate ring of the Grassmannian has a cluster algebra structure. So that was maybe the first result.
Is this the same as the one that they have in the paper, scattering amplitudes in the classic Grassmannian?
It'll be the same cluster structure, yeah. OK, so now I want to talk about the amplituhedron, and I'm just going to talk about the tree amplituhedron. So this, I should really write this out. This definition is due to Arkani, Hamed, and Trinka. So what we do is the following. So we're going to fix Z, a k plus m by n real matrix with maximal minors positive. And we're also fixing m such that k plus m is at most n. So this z is going to be used to give us a map that I'll call z tilde from the non-negative Grassmannian into another Grassmannian, grk k plus m of R. And this map is defined as follows. So if A is a k by n matrix, and I'm thinking of this as representing a point in the non-negative Grassmannian, then what we do is we map A to AZ transpose. And this is just matrix multiplication. So A is k by n. Z transpose now is going to be n by k plus m. And so we get a k by k plus m matrix, which we interpret as giving an element of the Grassmannian. I should say this map, to show, so you have to show that this map is well defined, namely this matrix has full rank, and that uses the positivity of the minors of Z. And now the tree, well, maybe just write one more piece of notation. So equivalently, if I write V as the span of k vectors, then what our map does is it maps the span of k vectors via Z to the span of the vectors after having applied z. Okay, so the map is really, really simple, although at first or second or third glance it seems kind of strange, or at least it did so to me. Okay, so I want to first just start by illustrating that this object generalizes many nice objects. Sorry. Sorry. I left off the definition. I left off the final sentence giving the definition. So the tree amplituhedron A, N, K, M of Z is the image of the map. So it's everything that you can get by applying Z tilde to the non-negative part of the Grassmannian. And so this is a subset of GR K plus M. Okay, so this is the amplituhedron. Thanks for the question. Okay, so now let me just mention that it generalizes lots of nice objects. So first of all, if Z is a square matrix, then the amplituhedron is just isomorphic to the totally non-negative Grassmannian. So we can think of it as a generalization of the totally non-negative Grassmannian. Now second, maybe people can't see. They can't really see if I write here. Huh? Okay, I won't write there anymore. So second, if K is 1 and M is 2, then this amplituhedron is a subset of GR13, which is P2, and what we get is a polygon in projective space. So let me just kind of go through the calculation. So we're in the K equals 1, M equals 2 case, and so I'm going to look at this map from GR1N into GR13, and the totally non-negative part of GR1N, namely projective space, is represented by points with projective coordinates non-negative. And we're mapping this row vector to the product of matrices. So this is n by 3. It's going to live in P2. So now let's think about what we're going to get in the image. So let's write EI. So EI will be the unit vector with a 1 in the ith position. And let's also write Z. So Z is this 3 by n matrix, and let me label the columns z1, z2 to zn. And so now in this case, EI is going to map to ZI, just that ith column vector. And now so EI can be thought of as a point in the non-negative Grassmannian GR1n. And now if we think about what happens as we let the AIs range over the non-negative real numbers, we're just getting a cone spanned by these ZIs. But now the fact that maximal minors of Z are strictly positive means these points in P2 are in a kind of convex position. So maybe they look something like this. And as the AIs vary over non-negative real numbers, you're getting this kind of cone spanned by the ZIs. And so you can think of this object as a polygon in P2. Okay, so any questions about the example?
I have a question. What is it? Why is it called tree? Where is the tree structure?
So I think that's maybe a reference to the Feynman diagrams. Yes?
It's what calculates the tree scattering amplitude. Okay. And at loop level, there is a generalization.
Okay, there is you can define it.
Yes, there is an amplitude for any number of loops, any number of particles, but it involves a double generalization, and Lauren's talking about
Yeah, the tree case, yeah. Okay. Okay, so we've seen that this amplituhedron generalizes the non-negative Grassmannian. It also generalizes these polygons in projective space. And if k is 1 and m is arbitrary, then what we get is what's known as a cyclic polytope with n vertices in PM. And I'm not going to define cyclic polytope because it's not really particularly relevant, but I'll mention just that they are important polytopes in combinatorics because they kind of are extremal in terms of maximizing faces given the number of vertices and the dimension. Okay, so this generalizes lots of nice objects.
You're in the cyclic polytope in there?
With, sorry, this is how I write, with n vertices in PM. Okay, so now let's recall that A n k m of Z is the image in GRK k plus m of this map Z tilde in GRK k plus m. Now, the image is full dimensional, and this Grassmannian has dimension k times m. So you might hope that on the left-hand side you can find a collection of k times m dimensional cells whose images would give a partition of the amplituhedron. And so indeed that seems to be the case. Now the case m equals 4 is most interesting to physicists. And in that case, there's a conjecture. So maybe, can I use kind of the top part of this board? OK. So m equals 4. There's a conjecture of Arcani, Hamed, and Trinka that there is a particular BCFW collection of 4K dimensional cells in GRKN non-negative whose images triangulate the amplituhedron. Okay, so there are explicit recursive recipes for getting these BCFW collections of cells. They're related to the whole BCFW recursion due to Brito, Cachazo, Fang, and Witten.
When you say triangulate, it's decomposed.
So-
Cells not in the same place.
So meaning that their images are disjoint and they cover a dense subset of this.
So they depend on Z?
No. So they don't depend on Z, even though a priori this definition depends on Z, and it's not clear that somehow the topology of this object shouldn't depend on Z. But nevertheless, the conjecture doesn't make reference to Z at all.
Right, but it does, it's very important that the Z's are positive. So if
Yes,
they're
yes.
positive, somehow the shape doesn't change as you move around.
Yes.
Is that a theorem? Or that the field
So that is a conjecture.
no, but that the
Oh, that it's well
you
defined?
say that the field does not change.
No, that is not a theorem. No, no. I mean, somehow, yeah, it's not clear. Yeah.
So like a cyclic polytope is a unique combinatorial object. It doesn't depend on a parameter.
So cyclic polytope means different things to different people, but usually it does have some parameters involved in terms of giving coordinates of the points.
Yeah, but combinatorially, they're
But combinatorially, the structure is the same. Yeah.
So what is it in the case of the polygons in P2?
Yeah, I'm going to get to that.
Okay.
Yeah, thanks. So, yeah, that's actually the next item.
What's the conjecture based on?
Well, I think they've done extensive numerical testing.
Well, I mean, it came from formulas for calculating scattering estimates for rational functions. And there's a long story for thinking about these rational functions associated with these geometries. So the fact that it works at the level of rational functions is provable from quantum field theory. The fact that this is geometrizing quantum field theory is the conjecture.
Now, is there some unicity or some additional property which would make it unique, this collection?
That would make, no, in fact, the collection is not unique. Yeah. I'm actually, in this talk, I'm usually going to say, so there's sort of one canonical one that is often used because it's kind of combinatorially nicest, but there's actually many collections here. So there's a recursive procedure you can do, but there's choices along the way. At the end of the day, it spits out a collection that should give a triangulation. Okay, so let me talk about the case k equals 1 and what the conjecture in that case is true. So let's recall that if M is a collection of k element subsets of 1 through n, then this is a set of elements in the non-negative Grassmannian where Plücker coordinates are positive if and only if I belongs to that collection. And now, in the case that k equals 1, the BCFW cells in the non-negative Grassmannian are all those of the form SMTNN, where M is 1, I plus 1, J plus 1, for 1 less than I less than J minus 1, at most N. So this is where so in k equals 1, our amplituhedron, Sorry?
Apples doesn't like this.
Oh, yeah, thanks. So for k equals 1, our amplituhedron lies in GR1, 5, because m is 4. So it's 4-dimensional. And so this gives a 4-dimensional subset of projective space. And the conjecture, which is true in this case, is that this collection of cells does triangulate the amplituhedron. And this case actually recovers a known result of Rambaud on cyclic polytopes. So it's true here.
And it's true for any M.
For any m, yeah. Okay. Okay, so this conjecture.
These are cells whose images on the Z tilde are also cells.
So I think that's not totally clear, although in a case that I'll talk about in a bit, it is the case.
So the sort of k equals 1, everything is linear, so it gets more complicated when k is larger.
Yes, yes. Okay, so a main open problem is that conjecture, but another is what is the topology of this object? So as we mentioned, the amplituhedron recovers the non-negative Grassmannian, conjecture to be a ball, and when k equals 1, it recovers cyclic polytopes, which are balls. So you might ask whether it's a ball in general. Okay, so now m equals 4 is a bit hard, although we're starting to have a reasonably good understanding of k equals 2. But maybe we should just start in an easier case and go to m equals 1 and see if we can.
There's loads of different cellular decompositions you can get in this way.
Yes, yes.
Just a small comment, Lauren. Even n equals 2 matters for the physics. Slightly indirectly, not, but it does matter. So
Right.
in fact, all the m's matter, but
Right.
all the
Yeah,
m's
so
up
we.
to 4 matter at least.
Right. So we understand a bit about m equals 2, but m equals 1 is the only case where we feel like we totally understand. So let's just go to m equals 1. Now, remember that this amplituhedron is a subset of GRK, k plus m. And now, for m small, we would rather kind of think about m planes as opposed to k planes. So we prefer to work inside GRM, k plus m instead. So the very first thing we're going to do is kind of re-describe the amplituhedron after taking orthogonal complements.
Now K would be arbitrary.
K will be arbitrary. K and n will be arbitrary, but now m will be 1. Okay. So we're going to let Z be a k plus m by n real matrix. So k plus m, remember, is at most n with positive maximal minors. And let's let W in Rn be the row span of Z. So the dimension of W is k plus m. And let's let B, N, K, M of W be the set of all things of the form V perp intersect W, where V runs over elements of the non-negative Grassmannian. And this is contained, this is contained in the sort of right dimension of Grassmannian we want. And the statement is that the amplituhedron is homeomorphic to this, if you like, B amplituhedron. The proof is not too hard. I'll just kind of explain the proof idea, which is that if you start on this side, then we're working with things of this form, V perp intersect W. So these are both subspaces of Rn. We're going to take the orthogonal complement in Rn, which maps us to the span of V plus W perp. And now if we apply our map Z, Z annihilates W perp, and we get Z of V, which is an element of the A amplituhedron. And you just check that the map is a homeomorphism restricted to this subset. Okay. So this gives us a way to think about the amplituhedron, but lying in a Grassmannian that we prefer to work in. And next, we can use these sort of ancient tools of sign variation from the 1950s to get a very nice concrete description of the m equals 1 amplituhedron.
So this Grassmannian is K and the end, yeah.
This?
Yeah, letter missing, right? It's K.
Oh, this is, sorry, so this is M planes in W, but yeah.
W.
Yeah, that was, I didn't introduce that notation, but that's what I mean. It's M planes, and they are contained in W. Okay. So let me go back and introduce some techniques that people thought about in 1950. So if V is a vector in Rn, we're going to let var of V be the number of times that V changes sign, and it's viewed as a sequence of n numbers ignoring zeros. So, for example, if V is 4, minus 1, 0, minus 2, then we change from positive to negative once here and never again. And we're going to let var bar of V be the maximum number of times that V could changes sign after choosing a number, so after replacing each 0 by whatever you want.
In other words, you perturb V a little bit, right?
Yes, exactly. So var bar, well, but so we have to take the max over this procedure. Yeah.
But each zero you change independently.
Yes, yes. So var bar of V, so what I want to do to maximize sign changes is make this 0 positive, and then we have 1, 2, 3 signs. 3 sign changes. Okay. Okay, so now the second theorem says that for W, so remember W we thought of before as the row span of Z. And Z had this property of positive maximal minors. So W we're thinking of as an element of the positive part of GRK plus M comma N. So we have, there's two statements. So the first statement is that the B amplituhedron, so the first statement is true for arbitrary M, and it says that the B amplituhedron is contained in the set of all elements of M planes in W such that for any vector in X, var bar is sandwiched in between K and K plus M minus 1. So, I mean, we knew already that this B amplituhedron lies in the Grassmannian of
Subscript of X is in GR.
M of W. So this B amplituhedron lies in this Grassmannian, and this is saying that it's contained in the subset where your var bars are sandwiched in between K and K plus M minus.
We have one subscript. It's implicit that the Grassmannian is defined by.
Oh, when there's only one subscript, then what I put here is a vector space. And then this means M subspaces of W.
Okay.
Yeah. Okay, so that's the first statement, which is a inclusion. And moreover, when M equals 1, you actually have an equality.
Var is not an important measure. It's only var bar, right?
This is var bar.
Wait,
Yeah.
wasn't that equal to K plus M for every M equal to?
I need to stay.
Yes.
W
So
and W.
for all W in X. Yeah, it's confusing because we're talking about, so we're looking at a collection of elements in a Grassmannian, but then given an element in the Grassmannian, that's an M plane, and you're actually looking at vectors inside that M plane. So it's confusing because we're like looking at vectors inside, well, yeah. So BNK1 of W is the set, so here M is 1, so we're looking at elements in projective space, the projectivization of W. And what you get is elements where var bar is precisely K.
So they're changing sign every time?
Well, W, so W is a K plus, yeah, so W is a K plus M plane, and it's saying that they, oh yeah, so K plus 1 plane, yeah, so it's saying they're, yeah. Well, we can have zeros here also. We can have zeros here also, but yeah. Okay. Okay, so basically, so in general, we don't know is the inclusion in 1 an equality, but the answer is yes if M equals 1 or, for example, K plus M equals N. Okay. Okay, so now I want to say a little bit about how this is proved. Actually, it's actually easy to prove it given results of Gantmacher and Krein from 1950. So and part of this was also simultaneously proved by Isaac Schoenberg and Anne Whitney in 1951. And actually, they didn't phrase it in terms of the positive Grassmannian because the positive Grassmannian wasn't around, but you can rephrase it after the fact that way.
What did they learn?
Matrices. Just like positivity of, well, okay. To be perfectly honest, I tried to look at their paper, but this one's in Russian, and yeah, and so maybe it's yeah. The paper of Schoenberg and Whitney, I think it's in English, but it wasn't available on MathSciNet, so I have to actually do my homework and go to the library. Okay, so part 1 of the theorem says this element in the Grassmannian actually lies in the non-negative Grassmannian if and only if var of v is at most k minus 1 for every vector in V. So it's characterizing the non-negative Grassmannian in terms of the sign patterns of all vectors that lie in your subspace. Yes, but there's also, I'm about to give another criterion in terms of var bar. But now this is var bar of W is at least K for all W in the orthogonal complement. So this positivity imposes a strong bound on variation of vectors in your subspace, and so upper bound on those, and a lower bound on the var bar of things in the complement. And there's a similar criterion for when you lie in the totally positive part. And if and only if var of W is at least K for all W in V perp. Take away 0.
So when you say for all V in capital V, do you mean in the vector space or just in the basis of that vector space? So are you thinking of
It really means, yeah, no, you really have to run over all vectors in that vector space. Yeah, yeah. So it's tricky. It's not, in one direction, it's not so easy to check. Or rather, if you find a bad vector, then it gives a good check that you're not lying in there. Yeah.
You mean non-zero vector?
Yes. Oh, although, yes. Oh, yes, yes, yes. Right. Whenever I'm talking about var bar, I'd better be careful about zeros.
Oh, it's less very hard. Yeah.
Yeah.
Yeah, but in one, the 0 is all right. If all 0 is very big, you can move a little.
Well, I think I need it here, because if it's all zeros, then my var bar is too big.
But not in the previous line.
In the previous, here. Oh, yeah, right. Yeah, that's true. Yeah, that's where I want it. OK. So now, so basically, this theorem will precisely give us this given the proposition I erased. So yeah, so let me just, I'll just write that down again. So recall that B, N, K, M of W can be thought of as, so that's V perp intersect W, where V is in GRKN non-negative. So this is how we can think about B, N, K, M of W. But now V is in a totally non-negative Grassmannian, and W is also coming from a totally positive Grassmannian. So we apply this theorem separately to both of these things, and we get precisely this inequality. And the fact that this is an equality here Okay, so the fact that we have part 2 comes from a lemma that was in an earlier paper of Stephen Karp, which says that if V is in GR1n and var of V is at most k minus 1 for all V and V, then we can extend V, namely throw in more vectors, to an element of GRKN non-negative. And so that's what you use in order to show that you have an equality here. But we don't know if there's an analog of this lemma if you replace the 1 here by something larger. Okay. Okay, so now, so thinking back to the ideas that we have for m equals 4, that there's this kind of BCFW recursion that gives you a subset of cells that whose images should triangulate your amplituhedron, you can ask, can you kind of mimic that procedure for m equals 1? And the answer is yes. And you can also ask what is the topology of the amplituhedron and ask whether it's a ball. So basically everything nice that you would expect is true for m equals 1. So in the last minutes, I'm going to tell you how everything looks. So, so there does exist some kind of BCFW recursion giving a triangulation of the m equals 1 amplituhedron. It's done in you can write something down in terms of play-bit graphs, which is analogous to what's done for m equals 4. But I'll just tell you what are the cells that we use to triangulate this object. Okay, so the stratification is the nicest thing you could possibly imagine. So I'll let sign bar and k1 be the set of all 0 plus minus vectors to the n, be the set of sign vectors sigma, such that var bar of sigma is k. So sigma is just a sequence of zeros, pluses, and minuses, but I can define var and var bar for that sequence, just as before. And sign bar nk1 will be all those sign vectors that satisfy this. And similarly, sign nk1 will be the set of sign vectors sigma, such that your var is equal to k. So for n equals 5, and k is 2, sine 5 to 1 is going to be plus, 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 minus, plus, 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 minus, minus, plus, 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 minus, plus, 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 minus, 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 plus, plus, minus, minus, plus, plus, and plus, minus, plus, plus, plus. Because here, I guess, yeah, I guess I just wrote out the ones with no zeros. Yeah. Okay. I'm not quite sure what happens, but. And so the obvious thing to do is simply to partition this set of vectors based on what is the associated sign vector. So let's let B sub sigma of W to be all elements in the NK1 amplituhedron such that sign of W is sigma. And so our amplituhedron is the disjoint union of these pieces. Okay, so
It has to start with positive.
oh, so by convention we start with positive since things are viewed in projective space. So we just make the arbitrary choice that the first coordinate is positive. Yeah, thanks. Okay, so now let me draw a picture. I'm going to draw a picture for n is 5 and k is 2. And so what does the amplituhedron look like? So we're going to draw a hyperplane arrangement H 5, 2, which is going to consist of 5 general position hyperplanes in R2. And we're going to label regions in their complement based on which side of the hyperplane it lies on. Yeah, okay. Okay, so I'm going to make my first hyperplane L1 down here, and then L2 is going to do this. L3 and L4, and then L5. And now, so now let me start labeling regions. So this region I'm going to label, so basically this big unbounded region out here gets the sign plus, 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 plus. I consider this region to be on the positive side of all hyperplanes. And so then this region is plus, 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 minus, plus, because we have just crossed over the fourth hyperplane to get from here to here. And then this is going to be plus, plus, minus, minus, plus, because we just crossed over the third hyperplane to get here, and so on. Plus, minus, 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 plus, 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 minus, plus, plus, and plus, minus, plus, plus, plus.
So you have chosen a particular geometry for those upper planes.
Say that again?
You have chosen a particular geometry for those
So the
position upper plane.
So the picture I've just drawn is general position.
Yeah, but there is more than one general.
Oh, okay. So, okay. Yeah, so in fact, what I'm going to draw is called the cyclic hyperplane arrangement. And let me I'll state the theorem, and then I'll say what cyclic hyperplane arrangement means. So the theorem is that B and K1 of W is isomorphic to the bounded complex of the cyclic hyperplane arrangement H n k of W, and the strata of the amplituhedron correspond precisely to the regions. Okay, so the cyclic hyperplane arrangement is some arrangement in general position, but more specifically, it's going to have coordinates which are given, which are chosen using W. So W is this totally positive subspace. You choose a basis for it and use that to assign coordinates in a particular way. It has the same combinatorics as something called the cyclic hyperplane arrangement, which you would get by choosing coordinates coming from a Vandermonde matrix.
When you say bounded to a bounded complex, do you mean like a complex of shapes?
So what I mean is take all of the bounded maximal regions and then take their closure. So in this case, this is unbounded, but all of this stuff here is bounded. And so the statement is that this amplituhedron, depending on W, is isomorphic to the hyperplane arrangement you get, which has this dependence on W. And the map is extremely simple. It's induced by a linear map. And this is the whole combinatorics of it.
For example, there is no pentagon among those regions, right? So it's all this.
Yes. Yeah, I think it's going to be simplicial.
No.
Or-
Okay, where it was quadrilateral, which is what we don't see.
You're saying there's
Oh.
pentagons, or there's none in this
Well,
example?
it doesn't seem, not in this example. If everything is supposed to be kind of independent.
No, there's no pentagons here.
So you're not going to get a hyperplane arrangement which comes from the sides of the convex pentagon, for example.
No, but why do you ask about
No,
pentagons?
it's just as an example of a hyperplane arrangement, which clearly looks different from this.
Oh, right. And also, in general, the bounded complex of a hyperplane arrangement could have topology that is not homeomorphic to a ball, but in this case it is. Yeah. So basically, everything that is expected to be true in the case m equals 4 is provably true here. We have a triangulation, and the topology is as nice as you could possibly imagine. I guess the main point is that these sign variation tools seem to be very powerful, and they're already helping a bit for understanding the case of m equals 4. So I'll stop there.
Thank you very much.